circuit resonance, circuit transient, sorry. Today we're going to be looking at double energy transients. That's just circuits which have both the inductor and capacitor included. I will treat with the exams towards the end of the class. All right, so it's not that I'm overlooking that matter, but I will treat with it towards the end. So let us get started. I trust you all had a restful weekend. So let's get going. So on screen we have a series RLC circuit consisting of your resistor, your inductor, and your capacitor. And going back from the definition that we give, here we're closing our switch at time t equals 0. And what we want to determine is what happens in the circuit after that, after the switch is closed. So we're closing our switch. We're closing our switch at time t equals 0. All right? So what happens thereafter? So first we want to just look at applying Kirchhoff's voltage law. And if we apply the voltage law, then we know that the sum of the voltages around the circuit is equal to 0. But of course, I can write these voltages in terms of the current. So for the resistor, so if we were to write these in terms of the current, for the resistor, we know that the voltage across the resistor at any point in time would be equal to the resistance times the current at that point in time. Again, the instantaneous current. For the inductor, we know that that would be L di dt. And for the capacitor, what we would have had is that I was equal to C dV dt. So it means that V would be equal to 1 upon C times the integral of I with respect to t. All right? And so we have our voltages. So we have VL and we have VC. All right? So those are our voltage expressions. So I can differentiate throughout with respect to t. So if I differentiate this expression with respect to t, then I have R times di dt plus L d2I dt squared plus I over C, or 1 over C times I. And just making the, and just to be clear, remember when we introduced the services of transients, what we said is that we first wanted to create a differential equation that represents the operation of the circuit. Yes? And that's exactly what we're doing here. All right. The other thing I want to note, if we go back to the original circuit, I don't have a source shown in this circuit. Yes? So there's no source here. However, even if there was a source, and let us say we had that equal to some source, V. Okay? When I get to this point where I differentiate, we will get back the same equation because, of course, the source there would just be a constant, yes? And as such, once we differentiate that, that would also be equal to 0. Anyway, Dividing through by L, just making the coefficient of making the coefficient of the second differential 1. Right? Doing that differential. We have d2i dt squared plus r over L di dt plus 1 over LC times I, which gives us an auxiliary equation of S squared plus R over L times S plus 1 over C. So this would be our auxiliary equation. And of course, once we solve this, yes, then we'll be able to determine the roots of the equation. What do you think? All right. Now, from our auxiliary equation, we know that the solution of this equation would be in the form a1 e to the s1 t plus a2 e to the s2 t. All right, we know that will be the general form. But this is true if and only if that is true. In other words, what this is saying is that S1 and S2, all right, so if this is true, what it would mean is that S1 and S2 are roots of the auxiliary equation that we have found, right? So this would be the solution if S1 and S2 are roots or the solution to that auxiliary equation. Now, our auxiliary equation is a simple quadratic equation. And so I'm going to use the quadratic formula to solve this equation. So the roots of this equation, S1 and S2, S1 minus R over 12. So we're using the quadratic equation, that's minus B plus or minus the square root of B squared minus 4AC, okay, over 2A. Right, so that's minus B plus or minus the square root of B squared minus 4AC over 2A. That's the equation we're using. So for the first root, S1, we have minus R over 2L plus R over 2L all squared minus 1 over LC. And just hold this for the time being. All right, let's hold that part for the time being. And S2, all right, so here we'd have the plus or minus. I'll use a different ink for that. All right, so we'll have here the plus and minus. All right, so for each of these roots, what I have is that they're in the form minus alpha plus beta and minus alpha minus beta. In other words, in each instance, this would represent beta and oops, and R over 2L would represent alpha. All right, so R over 2L is alpha, yes, and beta is equal to what we have here in the bracket. All right, so that's simplifying that or writing it properly. We have alpha is R over 2L. And if we look inside the bracket here, yes, we see that this also represents alpha. So this would be alpha squared inside the bracket. And 1 over LC, if you go back to what we did when we were looking at resonance, yes, this would be omega, all right? Of course, we went all the way down to F, so it would be 1 over 2 pi root LC. So here, 1 over LC represents omega. So with 1 over root LC, sorry, representing omega, then we have omega naught, 1 over root LC. So if we substitute those into our brackets, then we'll have beta is equal to alpha squared minus omega squared. All right. If you go back to the auxiliary equation, yes, remember that we are using our quadratic equation, yes, which is minus b plus or minus the square root of b squared minus 4ac over 2a. Yes, b from our auxiliary equation, b is equal to r over l. A would be equal to 1, yes, and c from our equation will be 1 over LC. All right. So in writing it in this form, writing it as we have here, all we're doing is to bring everything within the square root sign. All right. So we're dividing, if A is 1, then we're dividing everything by 2. Fair enough? So it will be B over 2. So it will be minus B over 2, which is minus R over 12. All right, so that's where we get that from. B squared, again, if I bring the 2 into the square root sign, then it becomes 4. Yes, so it would be R squared over 4L squared, or R over 2L all squared, which is B squared. Fair enough? And then for LC, A is 1. So we'll be bringing 4 into the square root sign. So it will be 4 over LC times 1 over 4, because I'm bringing the half into the square root sign. So I'll end up with 1 over LC. So that's how we get this equation here, or this expression here. Okay? Any questions so far? Okay. Now, this is what we have here. And the fact that we're dealing with a square root. Now we know that if you multiply two negatives, yes, if we're multiplying two negatives, then of course we get a positive, yes. If we find, well, no, let me not take it from that angle. Here, within the square root, we can find the square root of a positive number. Right? We can find the square root of a negative number. Right? Or we can find the square root of 0. So if it's positive, then it means that S1 and S2 would be distinct because this square root would be a distinct number. All right? So it means that I would be adding minus b, or alpha rather. I'll be adding minus alpha to a specific number. So it means that we'll get different values for S1 and S2. If it's negative, if we are finding the square root of a negative number, years ago we would have said, well, that doesn't exist, but we know here that we'd end up with an imaginary number. So we'd have j included. Then of course, if what's in the square root is equal to 0, then it means that S1 would be equal to S2. So in essence, what we are saying is that the current, the final current, will be dependent on the values or the auxiliary equation, the discriminant, sorry, of the auxiliary equation. All right. We're going to look at the three possibilities. Of course, those are the possibilities that I just outlined. All right. So what are these possibilities? As I just said, the first possibility is that the discriminant is real and positive. Yes? So in other words, alpha squared minus omega squared, omega naught squared, is greater than 0. Right? So in other words, we have a positive value for the discriminant. And that is true if and only if alpha is greater than omega. Well, in my world, that is not the case, but anyway, that's not for this evening's discussion. But this is true if alpha is greater than omega. If alpha is greater than omega, we will define the circuit, right? We'll define the circuit as being overdamped. So if alpha squared minus omega squared is greater than 0, what that means is that alpha is greater than omega. And if alpha is greater than omega, it just means that what's in the square root is positive. Okay? I will say that the circuit will be overdamped. Now, an overdamped signal, the solution will be in the form e to the minus alpha t, a1 e to the beta t plus a2e to the minus beta t. And note that this is the same expression that we had earlier with S1 and S2. If we multiply that, then we'll have minus alpha plus beta, which is, of course, S1. And for this one and that, we'll have minus alpha minus beta, which is S2. All right, so this expression is no different from what we had indicated earlier. So for an overdamped signal, if you represent that graphically, and since we're dealing with the current within our circuit, if I represent that, this is time, this would be your current, right? Then your overdamped let's try that again. Right, your overdamped signal. Still don't like how that one looks. So let's go again. Yeah. So at this point, we'd have I max. So that's the maximum displacement. And what do we mean by overdamped? Just tell me when you are finished with the graph.
Please, sir.
Now, let us consider a couple of things before we try and explain this whole damping thing. If I had an inductor and a capacitor, now let us say that inductor had absolutely no resistance. We know that's not true, but let's just make that assumption. If the inductor had no resistance whatsoever, and the capacitor also has no contact resistance, and I'm able to have that inductor connected to that charged capacitor, then what will be happening is that they would continually simply exchange energy between each other. And I'm oversimplifying the whole thing, but I'm doing so with the hope that you'll be able to appreciate what we're talking about. So they'll be able to share energy. So the capacitor will charge the electromagnetic field of the inductor, then that causes the capacitor to be recharged. The capacitor discharges again. So in other words, that sharing of energy really would represent, technically speaking, oscillations. So there'll be a continuous sharing of energy between the two, resulting in oscillations. So in effect, what you would be having would be that. Okay, oscillation. Now, when we introduce this whole concept of damping, The idea is that we would remove these oscillations. So we'll be able to get rid of these oscillations. Now, an overdamped system would simply speak to a system where more damping than is necessary, more damping than is necessary is used to remove the oscillations from the circuit. All right? So with the oscillations that I'm showing you here, we're saying if it's overdamped, it means that to take it there and it quickly dies out, which is what we have represented here. So it will go to its maximum displacement and then it will come back to zero very quickly. All right? Because, as we just said, it's overdamped, so you're using more damping than is necessary. So you're using more than what it will take or what is needed to get rid of those oscillations. So that's what we mean by overdamping. All right? The next possibility is that the discriminant is equal to zero. Right? And if the discriminant is equal to zero, this is true if and only if alpha is equal to omega. Okay? And if alpha is equal to omega, then it means that the solution, and of course, remember, all we're trying to find here is an expression for the current, all right? So I would be equal to e to the minus alpha t times a1 plus a2t. Under these circumstances, the circuit will be considered to be critically damped. Critically damped. And the critically damped circuit is one where we're saying that the minimum amount of damping is used to remove the oscillations. Or in other words, just enough damping is applied. And if we finish with this equation,
Just a minute, sir. Can go ahead now, sir.
okay. So for this one, we're to graph. All right. So the critical damping. Again, we have our maximum because it peaks. Yes. But because we are using just enough damping, it means that it will take a slightly longer period for the signal to die. But it is just enough. And then finally, the third option is that the discriminant is less than 0. So now alpha is less than omega, which means that what we have inside here is negative. And if I'm finding the square root of a negative number, then of course we're now going to go into the imaginary spheres. All right? If that is true, then the circuit is said to be underdamped, and the expression for I is of the form A1 cos beta t, and this is the modulus of beta t, the modulus of beta times t, and A2 sine the modulus of beta times t, and all of that multiplied by e to the minus alpha t. All right, and do we have this?
1 second, sir. Okay.
All right, cool. Okay, so the graphical representation, note what we have here is that it is underdamped. In other words, there is damping, but there isn't enough damping to remove the oscillations. All right, so the fact that there is damping means that the oscillations will over time die out. All right, but because it's not enough, it will cause these oscillations to continue. So, and I'm just going to increase the amplitude of the signal just for just to help us understand what is happening here. Let's do that again. All right. All right. So what you'll have is that there would be a decreasing, exponentially decreasing amplitude. So again, you'd have your I and you'd have your T. Do you have any questions? worried now. You know. It's the same way. I had no questions for the other two topics. Anyway, I will work with it. All right. We'll take this question for me. Just a minute. All right, write this question for me, please. Given that the capacitor in the circuit below, given that the capacitor in the circuit below right, given that the capacitor in the circuit below sorry about that, has an initial charge of 18 volts. Given that the capacitor in the circuit below has an initial charge of 18 volts, derive an expression for the current transient I. Let's go again. Given that the capacitor in the circuit below has an initial charge of 18 volts, derive an expression for the current transient I. An expression for the current transient I if the 20 volt source is applied at time t equal 0.
Sir, could you repeat the last part, please?
If the 20 volt source is applied at a time t equals 0. Got that?
Yes, sir.
All right. So the question is, we have a circuit here. We have the resistance, capacitance, and inductance that are connected. We are told that this 20 volt source is applied at t equals 0, and I want an expression for the current transient. All right. So what we're going to be doing is just looking at the general steps, all right, that we would go through for a question like this. Now, we just determined that the current expression will be dictated by the relationship between alpha and omega. All right? So, because that is the case, it means that we have to first of all determine alpha and omega, and based on their values, we would know what expression the current will have. The other thing we also need to note, I didn't mention it, but we kept talking about A1 and A2. And you have the choice, and well, for the example, I'm going to do it also. How do we get A1 and A2? As we did last week when we were trying to find the constants in our integral, yes? We noted that those values were determined by the boundary conditions. And the boundary conditions, we would have to determine those based on the operation of the circuit. All right? We had said that for the single energy transients, right? The same principle will apply here. So you have all done differential equations. And in doing differential equations, your teacher would have given you the boundary conditions. The difference here for networks, what you need to focus on is that you have to look at the operation of the circuit to determine what these boundary conditions are. All right, that's the only real challenge. So let's get back to our circuit. So here's my circuit. As I said, the first thing we want to determine are the values for alpha and omega. So alpha is equal to R over 2L. All right, so that will be 200 over 2 times 100 times 10 to the minus 3. Okay. And that will work out to about 1,000. Okay. Omega is equal to 1 upon the square root of LC. Right? Somebody work that out for me quickly. We have L, we have C. So let's find omega.
$866.133.
All right, so that's 866.133.
133.
All right. Everybody good at that? And based on what we have here, it is obvious that alpha is greater than omega. All right. So if alpha is greater than omega, is the circuit underdamped, critically damped, or overdamped?
Overdamped.
Overdamped. All right, good. Now that we have the values of alpha and omega, the next thing we want to find is beta. And what's beta equal to? What is beta?
Square root of alpha squared minus
Right? Remember, 1 over root LC is omega. So 1 over LC is omega squared. Okay? So beta is equal to alpha squared minus omega squared. And that gives us
1,802.72.
all right. I'm going to ask you to calculate that again.
Sir, can call it 500, sir.
Huh?
Can call it 500 and run it up. So answer 499.1.
499.8.
Excellent. So it's 500. All right. So that's beta. Now, because alpha is greater than omega, it means that I is in the form A, and I'm going to use A and B, okay? Alpha is, I is equal to AE to the minus alpha plus beta times T plus BE to the minus alpha minus beta T. And alpha we know is 1,000, yes? And beta is 500. So this would be A E to the minus 500 T plus BE to the minus 1,500 T. Isn't it beautiful to be able to take photos when I'm not around? Who was that taking? Who is that taking photos? Is that Mr. Busso taking photos?
No, sir.
All right. So remember, as I just said, we need to now look at the boundary conditions to determine the values of A and B. All right. So at the boundary conditions, at the circuit operation, we know that at T equals 0, what is the circuit current equal to? At T equals 0, what is the circuit current equal to and why? I don't expect you all to open your mic at the same time and be shouting at me.
0, sir.
Why?
The capacitor I go open, sir. So it's gonna be an open circuit.
The capacitor? Remember, the capacitor only behaves like an open circuit when we have fully charged it, eh? So I'm agreeing that it is 0, but I need a better answer as to why.
Sir, at T equals 0, the switch is open.
Eh?
At T equals 0, the switch is open.
No, but we close the switch at T equals 0. That's what the question said. We close it at T equals 0. Okay. What's the current through the circuit before we close the switch?
Sir, it is
0.
So before we close the switch, it is 0. All right. Now look at the elements that are in that circuit. What would ensure, which of those elements would ensure that the current is 0 immediately after closing?
The capacitor.
inductor, sir.
The inductor, sir.
And the inductor.
The inductor, not the capacitor.
Okay, sir.
As a matter of fact, if it was left up to the capacitor, the current would be a maximum upon closing, because it would be ready to discharge. You with me? So at the point of closing, we know that I0 minus is equal to I0 plus is equal to 0. So at T equals 0, we're going to substitute T equals 0 here and T equals 0 here. And we know that all of that must be equal to 0. Yes? So at T equals 0, what we know is that 0, which is equal to I, is equal to A plus B. Yes? Or in other words, this implies that A is equal to minus B. Everybody with me?
Yes, sir, so far.
Yes,
All right. Now, so that's, now we have two unknowns. So obviously we have to consider at least two conditions for the circuit because we have two unknowns. All right. So at t equals 0, so we have looked at the current in terms of what is happening at t equals 0. But we can also look at the voltage. So at t equals 0, when I close the switch, what did we start out by saying in general for RLC circuits? What rule did we use or law did we use? Huh?
KVL, sir.
Talk to me about the voltages as soon as you close the switch. Somebody said something just now? What is true about the voltages within the circuit at the point you close the switch?
Sir, the sum is equal to 0.
Okay. Well, it's not equal to 0. But what can you say about the voltages? What have I done by closing? What have I done by closing the switch? What have I created by closing the switch?
A closed circuit, sir.
A closed loop. All right. So if I have a closed loop, what do you know to be true?
The voltage, sum of the voltage is equal to the voltage drop across.
The sum of the voltages. Well, again, the sum of the voltages
In the circuit is equal to 0.
But why are you saying it's equal to 0?
Would it be equal to the
Because of
voltage source?
KVL, sir.
Would it be equal to the
K,
voltage source?
exactly. So if it's KVL, what we are saying is that VL plus VR plus VC, those are the voltages in the circuit, yes? These are the voltage drops. Do you agree with that? What's it equal to?
What is source?
The supply, which is, it can't be 0 because you have a supply. So it's equal to 20.
20.
Yes? So VL, or what would VR be equal to? What do we know about the current? What do we know about the current at t equals 0?
0, sir.
It's 0.
So what would VR be equal to?
0.
0. All right. So let me just go to another slide. So we know that VR is 0. So it means that VL, and what's the expression for the voltage across the inductor? What's the voltage across the inductor at any point in time?
LDIDT.
Huh?
LDIDT.
So L didt, that's for the inductor. And what were we told about the capacitor?
Initial voltage was 18.
So we have an initial voltage of 18. All right? So we know that at the time I close the switch, there's no voltage across the resistor because the current is 0. I know that LDIdt is the voltage across the inductor because the inductor will always have a voltage given by the inductance times the rate of change of current. Yes? And I know that the capacitor was initially charged up to 18 volts. So we have L di dt plus 18 is equal to 20. Fair enough? So it means therefore that L di dt is equal to 2 volts. Or which implies that di dt is equal to 2 over 100 milli. That's 100 times 10 to the minus 3. Yes. That's 2,000 over 100. So that gives me 20. And of course, it's amperes per second. So di dt is equal to 20 amperes per second. How does that help us? We know that I, what was the expression for I? So if I differentiate the current, so dt of the current expression, which was A e to the minus 500t plus BE to the minus 1500t. Yeah. I know that this now is equal to 20. Okay. So if I differentiate this, I get minus 500 A minus 1500 B is equal to 20. But earlier, we know that what's the relationship between A and B? What's the relationship between A and B?
A is
A
equal to
equal to
minus B.
minus B.
A is equal to minus B. So it means therefore that 500B minus 1500B is equal to 20, or B is equal to 20 over 1,000. Minus 20. Minus 20 over minus 1,000. All right. So it will be equal to 20 minus 20. Oops. Milliamps. All right, which implies that A would be equal to 20 milliamps. All right, so I now have A and B, so I can now write my expression. So I is equal to 20 e to the minus 500 t minus 20e to the minus 1500 t milliamps, or 20 e to the minus 500 t minus e to the minus 1500 t, yes, milliamps. And that would be your expression, the transient expression for your current. Any questions?
Yes, sir.
Go ahead.
On the previous slide, we differentiated the e to the minus 500t. Where did the e go?
This is all occurring at t equals 0, no? Sorry, I just jumped a step there.
Okay, I see it.
Okay. Any other question? Going once, twice, and it has gone. All right. So, folks, I'm going to continue with this particular question. I'm going to add a couple sections to it. The section B of this question, what I want you to do is to determine the maximum value of the current. So that's the first question. Determine the maximum value of the current. And then secondly, I want you to sketch the current waveform. All right? Anybody want to take a stab at that one? No? Come on, man. Look at the sketches that we have done so far. We're trying to find the maximum value. How could I determine the maximum value of this wave, of this current? What happens after we pass the maximum value?
It starts to decrease, sir.
All right, so it's increasing, and then we pass the maximum value, and it starts decreasing. Yes? Everybody cool with that?
Yes, sir.
Yes, sir.
Yes, sir.
All right. Now, if that is the case, if it's increasing, then it reached the max, and then it start decrease. What name do we give to the maximum value? Or at what point do we have the maximum value? Okay. What we call it?
Resonance, sir.
Man, look, man, me throw you out of the class, man. Resonance? That has nothing to do with what we're talking about here.
So repeat the question. Is it IMAX?
Yes, we're trying to find IMAX. But give me another name that you have applied to this maximum value.
Amplitude?
Eh?
The RMS.
The amplitude?
All right, I can work with that, but give me something better than that, man. Wait. Remember, you are the best mathematicians in the university. You are in engineering. So if we have a point where it reaches its peak and then start come back down, what do we call that point? Eh? What do we call that point?
Sir, where is it? The upper boundary?
Huh?
Vertex.
You use those terms in math?
Sir, is it the peak?
Is it the gradient, sir?
Is it the RMS, sir?
You use those terms in math?
Sir, is it the
Limit,
gradient?
sir.
Sir, would it be the upper boundary?
All right, you're all guessing now.
Sir, will be limit.
All right. It will be a turning point.
Gradient, sir.
No, it can't be a gradient, man. It will be a turning point. You have used that term in math, right?
Yes, sir.
And you have your turning point for your maximum and minimum curve. Now, say go. You remember those things? Calculus? It's calculus 101 we're talking about now, you know. All right? So if I'm dealing with my turning point, how do I determine the value at the turning point? What do I do?
Equation equals 0.
Huh?
Gradient equals 0.
Gradient equals 0. So what do I do? How do I determine the value at this point? What do I do in determining? All right. Let me ask
Differentiate
it
it and set
another way.
it to 0.
Thank you very much. So we differentiate the expression and set it equal to 0. All right? So the person who was saying gradient all along.
So that's what I was thinking, but
Right? The gradient would be right along the curve.
yes, sir.
But at the point where it is maximum and then starts to decline, that is your turning point.
With the gradient.
And what we say is that the gradient at that point is 0.
Yes, sir.
You with me?
Yes, sir.
All right. Oh, so we now need to differentiate this current expression. All right. So we are going to find di dt. All right. And set it equal to 0. Now, you have a choice. Since you're differentiating here, you're going to set it equal to 0. You would recognize that we don't really need to consider the 20. It won't change anything. But for the purpose of being totally accurate, we'll include it. So 20 times 500, I give us 10,000. So minus 10,000 e to the minus 500t. Yes. Plus, this will give us what, 30,000? 30,000 e to the minus 1,500 t. And we set that equal to 0. So because we had multiplied both of them by the 20, I'm just gonna take out the 20 and make life a little simpler. All right, forget it. So what we have here is 10,000 e to the minus 500t is equal to 30,000 e to the minus 1,500 t. Yes? Or in other words, e to the 1,000 t is equal to 3. Everybody clear with that? So t is equal to ln 3 divided by 1,000. Right? That gives us 1 point. You know what? Work it out for me now. Work that out for me, please. Come folks, we have one more question to go through here.
1.1 times 10 to the minus 3.
1.1?
1.1, sir.
1.1. All right.
Minus 3.
Well, it's already dealing with them small numbers. Yeah, and I'm going to crucify it. But I'm going to put 99 milliseconds. So it's 1.1. 1.099 milliseconds. Okay? So what this is saying to you is that the maximum occurs at that time.
Sir,
Yes.
how is it that you get minus 10,000 at the equation of the I over D?
500 times 20. All right. So now that you know the time at which it occurs, I want you to now substitute that time into this equation. So you're going to substitute the time, this time, yes, into the current equation in order to find Imax. And what is Imax? So make that substitution for me.
Seven point 698.
I don't know, you're telling me. So I'm taking you, say 7 point?
7.9. 7.698. Sir.
7.698. What do you want it to give me? I have a funny feeling it's milli, right?
Milliamperes, sir.
All right, good. Okay. So you make your substitution, you get your current. You're good. And then the last part of the question, I'll ask you to sketch it. Right? Now, they'll ask you to draw. So you don't need exact values. What I need for you to do is to show that you understand the concept. So first of all, what is this? What kind of circuit do we have here? What kind of damping do we have?
Overdamped, sir.
Overdamped. All right, excellent. Now, as time tends towards infinity, as time increases, which one of these gets smaller? Which one of them gets smaller quicker?
E to the minus 1500, sir.
All right,
Okay,
so
sir.
this one will be heading towards 0 much faster than this one, right? Agreed?
Yes, sir.
Good. So if this one gets smaller than this, what is it saying about the current? Would the current be positive or negative? As t increases, this one gets smaller than this, right? So is the current positive or negative? Come on, quickly.
Positive.
Patrick question. Eh?
Positive.
Must be positive, because this will be greater than this. Right? So on your sketch, what I would expect to see is something looking like this. Now, although in your notes, I was giving you things looking like that, right? I'm surprised nobody questioned it. But the reason it was drawn like that, is because there was no source. And based on the direction of the current, then the current will be flowing. It becomes negative to what we had assigned. All right? Anyway, so in this instance, the current would be like that, and then you would put that, this would be your 698, and this is your current in milliamperes, and then that's T. So that's your sketch. Any questions, students? All right, so let's take an example, another example. I mean, we can sit here and do examples all evening, but it's important that I know that you understand what you're doing. I don't want the same sort of issues as I saw coming out of Friday. Eh? Okay. Take the question, please. All right. All right. So here are the question. Here's the question associated with that.
Sir, I never finished through the circuit as yet, sir. Thanks, sir.
Okay. So I'll go through section A with you, and then you're on your own with B. I need to make sure I something here. Or another, I think I may be going to B with you. Do we have this?
No, sir.
3 more seconds, sir.
All right, sir.
Okay. So let's see if we can go through this together. First, I want you to determine in determining the expression for the current, what's the first things that we need to do?
Find
Need to
omega,
find
alpha and omega.
Find alpha and beta.
So we find alpha and omega. So quickly find alpha and omega for me, please.
Sir, alpha is 90 and omega is 140.
Yes, sir.
Alpha is 90. Alpha 90 and omega 140. I'm just taking
Yes,
your
sir.
words for that, you know. Okay. And there's agreement. So alpha 90, omega 140. So what's the relationship?
Alpha is less than omega, so the circuit is underdamped.
Okay, so alpha is less than omega, so we're dealing with an underdamped circuit. Excellent. So what's the general expression for the current? General expression for the current?
Sir, e to the minus alpha t.
Mm-hmm. I'm
Right.
listening.
A1 or A cos beta, cos
So
modulus beta.
I is equal to,
E to the minus alpha t.
so that's minus, oh, you know what? Yes, you're on the right track, but let us just do a couple of things before we do that, all right? Find for me beta.
Sir,
What is beta?
isn't that the other way around for the symbol?
What is beta? Calculate beta for me. Which is really mod beta.
107.238.
107.238. 24. All right. And you found that by the square root of alpha squared minus omega squared, yes? Modulus of that. Okay, excellent. Okay, so now I want the expression for I. What's the general expression for I? So you're going to put in these values now. So e to the, or, you all don't shout at once. Come on.
It's a e to the 90 minus 90 t times in bracket A cos 107 cos 107.24 t plus B sine 107.24 t.
Excellent. All right. So the only difference here is that when we compare alpha and omega, we see that alpha is, hold on, alpha is less than omega. I have it written as greater. Alpha is less than omega. Yes. Because alpha is less than omega, then we know that we have an underdamped system. All right. So the current expression is given by that. For the boundary conditions, what are the boundary conditions? What do we know?
Oh, sir, due to the inductor, I equals 0 at I 0 at t equals 0.
So at t equals 0, I is equal to 0. Since, of course, I0 plus equal I0 minus equal 0. Excellent. So if I put in 0 and I put I now substitute t equals 0, what do I end up with? When I substitute t equals 0, what do I get?
Sir, A cos 107.24 t.
That would be A cos 0, no? Cos t equals 0.
Oh, yes, A cos 0.
Plus
0, sir, cos sine 0. 0.
Exactly. So I'm going to put it in just for the sake of clarity. So what is that telling me?
A equals 0, sir.
A equals 0. So A equals 0. So what we are left with is that I is equal to e to the minus 90t. So I can now rewrite my expression because I know that A is equal to 0. Yes? What we have not determined is B. So I get e to the minus 90t B sine 107.24 t. Is there anybody who is unclear as to how we get this?
No, sir.
Okay, so we move on. Now that I have this expression, what else do you know? What other boundary condition do we know?
T equals 0, the sum of the voltages equal 40.
So at T equals 0, VL plus VC plus VR equal 40.
But you know
Good?
that VR is 0.
VR is 0. How about VC?
VC 0 as well.
Oh, you know that? Huh? How do you know that? Who said VC was 0? What happened? Who just said VC was 0?
Sir, me, sir.
Huh?
Gray.
Oh, Mr. Gray. How you determine that VC is 0?
Sir, just assume.
Well, that is a fair assumption because you are not told otherwise. Right? The circuit, the question does not indicate that that the capacitor was charged. So you have to assume that VC is equal to 0. The fact that I challenge you don't mean you're wrong, you know. All right?
Okay, sir.
So LDI dt is equal to 40. So di dt is equal to 40 over L, and L was 150 times 10 to the minus 3. So that gives me 4,000 over 150. All right? All right, 80 over 3 amperes per second. Everybody with me? So we now know that, so we can now differentiate. So we can find d dt of I, and we know that I was e to the minus 90t, yes, sine 107.24. Right, d, put d to that. And when you differentiate that, it must be equal to 80 over 3. And of course, in differentiating this, how are we going to differentiate this?
By part, sir.
Product rule.
Product rule. Exactly, product rule. So do that. And remember, all of this is occurring at what time?
T equals 0.
T equals 0. So differentiate, substitute T equals 0, and solve for it, please. Calculate B. Right. Of course, students, you can, I mean, based on what we have here, we know that once there's a sign component, that substituting T equals 0 is going to make it 0. Agreed? So it means that you really don't have to use the complete product rule. So it will only be where you differentiate the sign component. Are you with me? Do you understand what I'm saying?
No, sir.
if you use the product rule, you're going to differentiate this, yes, times what you have there, and then you differentiate this. Agreed? Therefore, the only part of the differential you would have to concern yourself with is 107.24 b e to the minus 90 t cos 107.24 t. In other words, only when you differentiate this. All right, let me take my mouth out of it. I hear the deafening silence. So you go ahead and use it because they are product rule. Go ahead for me. And substitute t equals 0. Are we finished? So what is b equal to?
0.247.
So what you ended up with was, I'm assuming, 107.24 b
Equal 80 over 3.
equal 80 over 3. That's what you ended up with, right?
Yes, sir.
All right, cool. So with practice, you'll see the shortcut. So b is equal to
0.247.
0.247.
sir.
So that is 247.
Oh, 249, sir. My mistake.
249 point. What come after the 9?
I was already running up, sir.
All right, don't round up for me. 248 what?
0.66.
So 248. 0.66 milliamperes. All right, so much number we can get when we use this?
Yes, sir.
All right. Good. So it's 248.66 milliamps. So it means that I is equal to 248.66 e to the minus 90t e to the minus 90t sine 107.24 t. So this is your current expression. Okay? Everything that we did in the first example, meaning everything that we did in the first example in terms of getting for the maximum, I think that was the second part of the question. Time taken to reach a maximum. For T max, we'd set di dt to 0. Yes? And find the corresponding current, the corresponding time. And once you have T max, you substitute for I max. All right? And then, of course, if you're sketching the curve, again, you know that it is underdamped. So what we are expecting, and you also note that you would get the first oscillation would be positive based on what we have here. Agreed? The 248.66. So it means therefore, that shouldn't be happening. Anyway, it look like I used up all my slides. Just a moment. All right. So your curve it's oscillating, so it means that we'd have our first positive going up and then it dies down. All right. So it must be in an exponential envelope. So that's what we'd expect from the sketch. And then your maximum is whatever you calculated I max to be equal to. All right. The second part of the question, where you increase the value of R. Now, increasing the value of R, what that would, just quickly calculate for me. If you doubled R, calculate the value of alpha and omega for me. Because I want to make a point there. Just calculate alpha and omega.
Just R alone, sir.
I think that's what the question said, that we doubled R. That's yes, resistance is doubled to 54. So I'm saying find alpha and omega.
Alpha is not greater than omega, sir.
No, I want the values. So what's alpha?
180.
180. And omega? Would be the same,
omega.
right?
Yes, sir.
Omega would be the same. What was it again?
140.
140. Okay. So now alpha is greater than omega. So what is that saying to us? In terms of the current expression. What's the condition of the circuit?
Overdamped.
No, overdamped. And I did this because I wanted now to highlight the fact that damping in your circuit is produced, or increased damping is produced by increasing the resistance in your circuit. Right? So that's one way of increasing the damping. So if you want to remove the oscillations, you can increase the resistance of your circuit. Increase damping. All right. And guess what? That is the lovely sound of the end of transients. We will make use of the time on Wednesday. So I will come, I'll field a couple questions, and then we'll just move on to the next topic. We're slightly ahead of schedule, but given all that is happening, we will try to use the time as best as possible. So if you have questions, I will take them now, but I will also need to mark the register. So, and you know, under normal circumstances, I will have just ignored. Just a minute here. Okay. But I think I have said it enough. So whoever has their ID number there, as far as I'm concerned, they don't exist. So let us get cracking with the register. And I'll just mark who I can identify. All right. Now, while I do this, any queries, any questions about the question that you'll do this evening or later this evening?
Sir, I lost you for a second there. Could you repeat that?
Now I'm saying any questions regarding the question that you'll be doing immediately after this.
Sir, will it be of the same capacity as the one that was, in part on the paper?
I can't give you one whole weekend to do a question, Miss particular.
No, sir, I never mean if it's going to be the exact question that was on the paper, I mean if it's going to be the 2-port.
Yeah, man, I can't change that. I couldn't change that. All right, so let me just quickly go to Ms. Campbell. Ms. Chen, you're here? Marcelo Clark. Is he here? Yes, Marcelo Clark.
Yes, Chief, I'm here.
Okay. Yes, I see you, Ms. Chen. Is that a question, Ms. Chen, or are you just saying that you're here?
Saying that I'm here, sir.
Okay, I can hardly hear you. Okay. Davis, Stefan? Absent. Okay.
Present, sir.
Okay. All right. First, yep. Grant Gray Jeffrey. Yep. Johnston Antonio.
Here, sir.
Kenyatta is here.
Yes, sir. Kenyatta Johnson, sir. Here, sir.
Yeah, man. Noted. Let's do this. This bench, yeah. File in. All right. Jerron Morrison is here. Absent. Phillips. Yep. Ramsey.
Present.
I'm going to see the name as well as Ramsey. Mr. Ramsey using another name. I don't see you here, so. All right, somebody answering for you, but I don't see a name there. All right. Yep. What's done there with? So Wilson left us. All right. Okay, students, as I indicated in my message, the question will become available at 7:15. You'll have your usual, you'll have 30 minutes to do it and upload and submit.
Sure.
And then you will upload by 7:15, 7:45. All right. Yes, Mr. Kamika.
Oh, I'm saying that I'm here. I didn't hear my name.
Yeah, man, I checked too.
Oh, okay.
All right.
Sir? in regards to Wednesday's class, will we move into the next topic or will it be a tutorial?
Next topic, man.
Okay, sir.
Okay. All right. So that's it for the lecture. Yeah. All right. Have a good evening. And as I said, the question will become available at 7:15. All right. Take care. Bye-bye.